prendió? Sí. Esta voy a subir de aquí. Ah. Luciano. Sí. Okay. There's something you learn as a particle physicist when we work with large experiments is when you see wires on the floor, remove the wires before you walk. So, okay. Hello, everyone. I'll switch again to English, and then maybe if you have questions, we can go in Spanish sometimes. But now we are here for part 2 of our machine learning lectures and tutorials. Now, what did we cover last time? Last time we talked about what is machine learning, right? What are the goals of machine learning, and then what sort of algorithms are useful in this. And then we drilled down and we looked into some specific goals. So let's just recap real quick what it is we've done. So what is machine learning? It's the study of algorithms that improve with experience. They learn like little children, but you have to train them and teach them for them to do useful things. So in this case, your tasks can vary. It can be either classification when you're trying to figure out whether a particular object is of a certain kind, or it could be something else if you're trying to estimate some continuous function. That would be a regression problem. Okay, so we looked at some more details. We saw that there were some commonalities. There were some fairly commonly used loss functions. And we did note that this was not the only kind, right? But these are the ones that work empirically. So it doesn't matter if it's boosted decision trees or neural networks or whatever else. There's something in common is a type of a loss function. And what you were doing, right, is we're trying to minimize empirical risks. You want to make less errors. So as you're training, right, you can change various parameters of your model so that you achieve a lowest error. And we looked at this in the context of classification, where we saw that the goal is to separate two densities of two classes. One we can call signal, and another we call background. And there's going to be some decisions to be made, and the place where the optimal boundary is to be determined. So ultimately, you're in control of what you're doing. But what you're trying to do is minimize a certain error rate. And as we saw in the practical examples, if you remember yesterday, we saw that you have errors of two kinds, right? Because you can misclassify each of these classes, right? You can call signal background, which would be over here, or you can call background signal, which would be over there to the right of your boundary, right? And that's when we looked at things like the confusion matrix, when we made our first classifier. So then we proceeded to look a little bit more into this. What's the cost of being wrong, right? And for now, we assume that the cost is the same, right? That the cost of choosing one or the other is the same. But as we also noted, in some cases, especially when you're talking about something like outcomes of the medical analysis, one can say, oh yeah, you're going to die tomorrow. That's a pretty grave thing to say. So you want to be sure about that, right, if you're going to make a statement like that. So in that sense, the cost is not always the same. So keep that in mind. And then we looked at I just introduced one example in particle physics where we made a Nobel Prize winning discovery of finding this Higgs boson. And in fact, I hopefully convinced you that without machine learning, you wouldn't be able to see it by eye, which now you can. So what we looked also is in this whole idea of deep learning, how it has come along. We didn't actually cover neural networks yet, which is something we're going to hopefully get to later today. If not, we'll do that, most of it, tomorrow. But we might get to that today, depending how quickly things go. And we saw that was a big shift, right? It was a big shift in performance, which is why, even though neural networks has been around for a while, the modern variants are much more performant than, let's say, their counterparts from 10, 20 years ago. We looked at detail of one of the classifiers, one type, so decision trees, right? Because they're very easy to visualize. And hopefully we've all learned how to read them, how to make them, how to understand how to build them, which was really the idea, is actually to open up the box, open up these models, and demystify them. There's nothing mysterious about them, right? And we can at least understand their structures and also motivate why they work and how they work. So that's where we started. Yesterday we looked at this example of playing golf, and we made another one on breast cancer, if you remember. And we talked about how to build a tree, right? In the end, it all came down to subdividing the parameter space, right, of your input attributes, and continuously, like incrementally, recursively building spaces that are more and more pure. So they're more and more of one class and then the other, and as different from the other class, right? And we use some ideas from information theory, such as entropy, and to basically define how the algorithm figures out that the next decision, right, is better than the previous. So, okay, so that's what we did yesterday. Today, I'll give you an idea what we're going to do. So we're going to start in the same place, right? We learned how to build a single classifier, but now we're going to kind of get a little bit more modern times. In modern times, nobody really uses single classifiers anymore. Nowadays, it's typical that you use ensembles of classifiers. Now, that could be ensembles of all sorts of things. Could be ensembles of trees, could be ensembles of networks, could be ensembles of rules, whatever. So, but it turns out that, just like, an army of soldiers is better than a soldier, a single soldier, and so is the same story here. It's true that oftentimes ensembles of classifiers perform much better than a single one. So we'll talk about that. We'll talk about how to boost performance of classifiers, this idea of boosting, which applies actually to all kinds of classifiers. We'll talk about performance metrics. If we have time, we'll talk about feature selection, and we'll introduce neural networks today. That's the goal for today. It's a lot, so if we don't get to something, we still have quite a lot of time tomorrow. So we'll do that, and we'll also try to do a little bit more practical stuff, just like yesterday. Okay. All right. So let's begin. Ensembles. How many of you have ever played an instrument? Okay, quite a few. Anyone who's ever been part of a band? No. Or a choir? Well, again, like I said, in this particular situation, a single classifier like a decision tree, is not as performant. Even though it works as your sort of first try, it's okay to begin. But if you want to get to like where the modern algorithms are, at least when it comes to tree-based methods, their ensembles are sort of the state of the art. Now, what does that mean, right? What that means is that if you can think of each one of these classifiers as something like a weak predictor, right? He's going to be better than random guessing, and that's the definition. He has to be even marginally better than random guessing. But there is a nice sort of theorem that says that even if each one of these guys is just merely better than random guessing, right? They're just pretty weak. If you put them in an ensemble and you train that ensemble, you can end up with something pretty good, right? So because what you're going to do is you're going to apply some sort of a function of these guys, right? And there is a nice paper about that you can look at. But there's a few different ways and a few different things, a few different types of ensembles that people have thought about, a few ideas that you may have heard about since they've been around for maybe about 15, 18 years, so this is not necessarily new. But for example, this one idea called bagging, that stands for bootstrap aggregation, is the idea of a bootstrap sample, right? I know how many of you are familiar with the idea of a bootstrap, but essentially it comes down to just basically have some sort of some randomly chosen sample from your set. So you don't train on everything, you just train on some part of it, which is a bootstrap, right? And you train each of your classifiers on such bootstrap, right? Now that in itself works, reasonably well, but then there are other ideas on top of it that have been really useful. So one such idea is called a random forest. Right? Now, the word forest should kind of be intuitive. right? Because we were talking about trees. Now we're talking about a forest, right? So forest means a collection of trees, right? Now, why is it called random? Is because in the case of a random forest, you also are doing this bagging, right? Again, this bagging with this sort of trees that are, you can think of them as randomized. And there is an additional idea here. There's an additional sort of probabilistic idea, a little randomization part, which is whenever you get to the split. You remember when we were building the trees, right? There was each decision node, and there were splits. And at that time, all the attributes participated. They all competed with each other, right? So here, instead of doing that, instead of them all competing at every single juncture, only random subsets of them compete at that juncture, right? So it's a way of introducing some sort of randomness in the process. Now, you may ask yourself, why would you do that? Why would it help to introduce these random ideas in this, right? And a lot of it actually comes down to something we're already familiar with, right, in our daily lives. Like, as you can see, we're all a little bit different, right? And if we had an army of identical, people doing the same thing, then the outcomes would all be the same, right? So if you have 100 identical classifiers, this is as good as a single one of them. But the moment you introduce a little variation, right, they will all be, one be a little bit worse here, another will be a little bit better there. But if you have them all together working as a team, then in the end, if they're all asked to, as a group to say, hey, is this a cat or a dog? Because of this little variation that you have among them, you'll end up doing better than a single one. So that's the basic idea, right? It's almost like some kind of little genetic variation, if you want to think about that way. By the way, there's also a very nice machine learning algorithm called genetic algorithms, which I haven't mentioned yet, but there's also some ideas from the sort of randomization and genetic evolution that people have built actually entire machine learning algorithms from. So that's what random forest is. They're actually pretty good, and they have pretty good performance, and they're pretty robust. So that's a pretty well-known method. Another type of an ensemble, and also an idea, is something called boosting. Now, the idea with boosting is that every tree, so every one of these classifiers, you introduce some sort of a reweighting scheme. So you say, okay, I'm going to start off with one classifier, right? And then I'm going to, reweight my training set in some way, right? And I'm going to build another classifier on that reweighted set. And you're going to do that in some way until you arrive again at a collection of an ensemble of classifiers that again differ from each other, right? It doesn't mean any one of them is going to be that great, right? But all together, they're going to be pretty powerful. And there's some nice theorems about it. So usually this idea of boosting and all that is connected with decision trees. You probably heard of boosted decision trees, right? BDTs, right? But in reality, it doesn't have to be, right? Boosting also applies to other algorithms as well. Okay, so that's sort of the general idea. And in fact, there's one person that's pretty much responsible for a few of these ideas. It was a very smart man, unfortunately he's no longer with us, Leo Breinman, who came up with the idea both of the random forest and also the idea of bagging. And this was in the early 2000s. So just for completeness, I'll just leave that in front of you with some, you can look up the original papers. If you haven't read them, I recommend you to have a look. The interesting thing is that people didn't know for a while why boosting worked as well as it did. It was actually took maybe a few years to figure it out. So empirically, it worked really well. And it wasn't really clear for everyone why. And only later people actually got an idea why. But this original paper is really good if you want to understand this idea. But the important thing is that it's all about adaptation, right? This idea of this idea of adapting to the environment and adapting of the model to what's going on. Okay, now I will talk about just one type of boosting, and then there's many types. So they all differ in some small way. But we'll cover like maybe the most sort of popular one, and then you can look at others whenever you like. So there's something called adaptive boosting, or actually the algorithm itself is called AdaBoost. That's sort of a classical name. And the idea is that when you train, you do it in stages. So it's iterative, right? There's an iteration. Each step is an iteration. And the idea is that you introduce some weights. And let's say you build a classifier. Let's say you build a decision tree, right? As we saw yesterday, that tree is going to make mistakes, right? It's going to make mistakes of the first kind and the second kind. It's going to misclassify your classes. And the idea is that you do it once, and you look at the events where, or those sort of instances where you made a mistake, right? And now you reweight your original training points or your training sample to give more weight to these instances where you misclassified, right? So that the next classifier that you're building is going to have, it's going to have a different weighting of these things. So it's going to build something different, right? It's going to be a little bit different now. And you do that once after, one time after another, and you do it as iteration after iteration after iteration after iteration. At some point you stop, and you end up with a collection of trees, let's say, right? And then you use them all together in some weighted ensemble to predict, to classify whatever it is you want to classify. So that's the idea, right? It's a pretty straightforward algorithm. Actually, if you want to write it down as an algorithm, it's right here, right? You basically repeat this k times. So you start with, let's say, a decision tree, which is, has some function of weights. Initially, they're all, all 1. And then you start computing the error on this set. And then there is some function, which is, a logarithmic kind. And what you're doing is you're increasing this weight where where you've made a mistake relative to those that are correct. And in the end, you're looking at a weighted average. That's basically the original algorithm, right? Any questions? Can everybody follow this so far? Yeah, okay. So this is AdaBoost. All right. Now, let's see. Let me make a quick example, right? And let me see actually how well this is going to work. The example itself I'm going to take from particle physics. Now, I told you about Higgs boson last time, right? So there's many different ways you can, that this Higgs boson is going to manifest itself. So you produce it, and then it decays into something else. It's like a mother particle that produces daughter particles. So sometimes it decays into 2 Z's, one of them being virtual. Z boson is another particle, right? And that particle itself doesn't live very long, right? And in the end, it decays into 4 other particles called leptons, right? Leptons are, muons or electrons, so, particles we're already familiar with. So particle physicists actually observe the leptons, right? We get these guys. Now, we also invented a fancy way to show what happens. They're called Fineman diagrams, right? Before, these were like huge integrals and calculations nobody would be able to follow. But Fineman figured out that you could actually express that as a nice, concise-looking diagram, right? So, 2 particles come in, out comes the Higgs, decays into this, Z boson and another virtual particle, and in each one of these decays into, an electron or a muon, right? So that's what the Higgs would do, right? So what we see in the detector are 4 particles of this kind. And to figure out if we saw the Higgs, we would add them back together, right? We would add the two electrons over here, or 2 muons over here, and see if that makes a Z boson. We know the mass of that particle. And then together we add another 2, and then we see whether we can see the Higgs. Unfortunately, that's not the only kind of process that produces 4 particles of this kind, right? So there's another process, right, that makes exactly that without Higgs. The Higgs is not involved in this other process, so it's a background. In the end, they look the same, right? If you just say, give me 4 leptons, you may get this or you may get that. You don't know what you're going to get. So the question is, can you build a classifier that's going to distinguish one from the other? Can you build a classifier that's going to find the Higgs, and throw away, let's say, the background, right? So that's the idea. And let's say we really wanted to simplify this and say, all we're going to do is we're going to worry about 2 variables. The mass of this combination of these 2 guys and these 2 guys. MZ1, MZ2. Right? That's all. We're not going to introduce any other variable. All we're going to look at is the mass, meaning what happens when you combine these 2 particles together. Should be around the Z. This one should be around the Z. In this case, it doesn't have to be. Right? Here, you don't expect them to come from a Z. Right? So, well, actually, sorry. They come from the Z, but you don't expect them together to come from the Higgs. So you don't know that. Okay. So what happens? Let's say I built a decision tree. Right? Let's say I did this AdaBoost algorithm. So the first tree is going to be something like this. Here is some boundary right? It looks pretty simple, right? It just says everything to the top is, signal, to the bottom is background, something like that. Now, if you looked at where this made mistakes and said, let me reweight my training sample, then the next tree would look like that. And if I continued, it would look like this. And this is what the first 6 trees look like, right? No, it doesn't really tell you much, right? You see things have changed. Each one of them does something different, right? What's going on? Okay, well, let me give you an animation of the first 100 trees. You see, they all kind of go up and down. They change. They're all a little bit different, right? So I'll let you stare at that for a second. Okay, now, here comes the interesting part. The interesting part is, let's look at when we average over this forest that we just built, right? And you start to see an interesting pattern. So this is when you average the 6 trees, right? There's some structure starts to show up, right? And then as you keep increasing the number of trees, 50, 100, 250, 5,000, at some point you really start to see that there is an actual boundary, right? There's an actual boundary that this ensemble, this average ensemble, is able to pick out something that, an individual tree really couldn't, right? So even in this really simple two-dimensional example, you can already see this. And this starts to make even more sense when you look at what these things actually look like, right? So here is, for example, the Higgs. You recognize that shape? That's what the Higgs sort of would look like in this particular space. And this is the other one. The other would be randomly kind of distributed over here. So this is what the actual sort of optimal boundary would be. And this is what you start to approximate with this ensemble, this boosted ensemble. You see? So that picture is not really a surprise. Yeah. But the way you got here is by starting with one weak classifier, right? And then building more weak classifiers and then use them all in ensemble to get something pretty powerful. Right. Any questions about the example? Yeah. Okay. Well, actually, what we'll do is we'll do something fun. We'll maybe stop here, and no, actually, let's do one more thing before that. Actually, you know what? Yeah, let me skip to that. Let's actually go back to the example we did yesterday where we built the trees. So we can actually, instead of building a single tree, let's actually build a boosted classifier. So let's take it one step further from where we were yesterday. So for that, let's go back to what we were doing. Now, there is a small change. The change is that I've changed the account. Okay? So there's also another tutorial going on at the same time, and I promised that they can use the other account. So those of you who had numbers between, let's say 2 and 30, you should just switch. By the way, maybe people change places, so maybe I'll give you new numbers. And we'll use new accounts. For those of you that weren't here yesterday, we're going to use a service called Swan, which is, for the purpose of this example, we're just going to use the terminal. So don't worry about what that is for. But tomorrow, we'll use Swan for Jupyter notebooks and fun things like Keras, whatever. Okay, so let's log in. Before we do that, let me just assign you numbers again. And maybe if whoever is sitting on their own, if maybe you can go and sit together with someone, that would be good, since we have a lot of people. So I guess you would be number 2. Can you guys work together? Is it okay? Yeah. Okay. So 3, 4. Okay. I guess you're on your own. 5, 6. Oh, maybe can you pair up together? Okay. So 5, 6. You guys together 7, 8. Anybody need a partner? Okay, you can be 9. Yeah, and then 10, 11, 12, 13, 14, 15, 16, 17, 18. Lucas, you're 19. Oh, you're not. Okay, so 19 for you. Or actually, would you mind to work with someone there? Okay, So then 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So you guys are 29. You're 30. Now, for you guys, we're going to go back to the ones which were yesterday. If you remember what they were, that was stat LR. And you start with 31. So you'll be stat LR 31. And the password is at -1. Okay. So 31, 32, 33, 34, and 35. Okay. I added a link, by the way, to yesterday's tutorial. I also added a link where you can register. So at some point today, if you can do that, that would be great. Yeah, you don't have to do it immediately, but you can do it today. Okay, so I'm going to do this with you. Right. So I'm going to go to Swan 001. You can pick Swan 00, whatever number, 1, 2, 3, 4. Try to pick different ones. Okay, if you're already logged in, log out, because we're gonna, we're starting anew, right? So let me log out. Yeah. Just log out. Yeah, development lineage. But if you're already in, you should. Yeah. Okay, so mlearn at 01, 00. So the password is whatever that number is. 1, just subtract 1. So mlearn. If you're mlearn 20. Then your password is mlearn at 19, right? Yeah. Okay. And when you log in, you're going to see something like this. Okay. And how many of you have logged in already? Okay, so does anybody still need more time? Yeah, well, let's wait for everybody. So. Yeah, so instead of this, you need to write mlearn.
Yeah, but I have not seen it yet.
Mlearn, mlearn. What was your number? 14? Okay, and then mlearn at 13 is your. Yeah. Okay, anybody else need more time? Okay, we'll wait. Yeah. Okay. Is the old one? So you should log out?
Yes, I log out.
Log out, wait. And go back to previous location. That doesn't want you to do it. Maybe you have to clear your cache or something like this. Yeah. Yeah. mlearn 05.
Oh.
Yeah. Anybody else have a problem logging in? I can try to help. Okay. If not, I'll just wait. Let's just wait another minute for somebody to log in. But basically, what you want to do once you're here, so you don't waste time, is to open up a new terminal. So just click on that. That's going to open up a terminal like this. If you have any trouble, just raise your hand. I'll try to help. No, okay. Now, because those of you that are using new accounts, you're going to have to check out the tutorial again. So I'll put that up again also. That's quick, though. So here, you want to type this thing. Well, I already have it, but wait. Yeah. Okay, so you want to type this. Let me increase the zoom. So to get it, you need to type git clone and then that address, and then hit enter. I already have it, which is why it doesn't want to do it for me. But
no, I couldn't get in.
oh, okay.
It entered directly to the address.
It still remembers it. You might have to clear your cache. Or do you have another browser, or do you have like Safari or something? Then you just switch to Safari.
Does it work?
Yep. So you have to go here. Yep. Okay. So did everybody get the tutorial? Anybody still need more time? So if you do it, then you will have it here. And here you want to go to this tutorial. So change directory tutorial _ unam. Inside, you can have a bunch of stuff you can ignore for now and go to C50. So change directory to C50. Right? That's the tool we used yesterday. Right? So you can see where you are inside of the C50 folder. And here's where our magic happens. Okay. How's everybody doing? Are you already there? Or getting there? Okay. If you need help, raise your hand. I'll come and help. Nope. No? No. You should go to, no, you need to check out, you didn't do this command, git clone.
No, I didn't.
Yeah, you need to do that. Yeah.
You went to
Okay. So you want to do this command, the very, very first thing. Yeah. You already there? Come on. Yeah? Bien? Okay, excellent. So now you need to go. Oh, you're already there. Perfect. Perfect. Good? Okay, so we're just waiting just for a few more people to get to the same place. You guys are ready? So here you want to go to C50. Okay, great. Excellent. Everything good? 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 Good. Yeah?
I don't find those.
Oh, here it is. You're in tutorial unam. So just go there. CD there. And then go to C50. Okay. Excellent. Okay. So did you manage it? Okay. What?
Could not trade work.
Let's see. Okay. Ooh, oh, you're in some, I don't know where you are.
I don't know either.
Okay, try now. Well, because you went somewhere you cannot, you went outside. Okay. Now you're okay.
Thank you very much.
So, no problem. Okay, so what did we do yesterday? Yesterday we built a tree, right? Does anybody remember how to build a tree? So we did this. Let's go to straight to the breast cancer example, right? That's the one we left off yesterday. So let's give it the name of the file. Maybe, is there somebody here who wasn't here yesterday? Or was everybody here yesterday? Okay, a few people, okay. Well, basically, if you look at the example for breast cancer, and if you look at the names file, that's your configuration file. If you go to the very end, that the only relevant information is here. It tells you that there is 2 classes, have cancer, don't have cancer, benign or the other one. And then you have one variable, which is just some code that's ignored. That's some patient number. And then everything else is just different variables, attributes, which you can use to try and distinguish, right? That's all it is. OK, so let's build a tree. Again, so ./C50, and then you give it the name breast cancer, right? So if I hit enter, that's going to build the tree we built yesterday, right? Which is right here. All right, everybody remember that, that tree from yesterday? OK, so now let's do something fancier. Let's build a boosted ensemble. Now, sounds like it'll be a lot of hard work to do, but actually, with this specific classic car, all you have to do is add a little prefix. So if you add a -b, or a -b before this, what it's going to do is it's going to build you a boosted classifier. So I'm gonna store that in the output somewhere. So I'm going to call it breast cancer, and I'm going to call it a BDT, right? Just for fun. Hit enter. Ooh, it's done already. It's quick, huh? OK, now let's look at what happened. Boosted decision tree. Yeah. OK, so now let's look at what happened, right? So the first thing you see is the usual, hey, I'm C50, right? What time it is, in some interesting time zone. Then it says, I'm going to read 500 cases, 10 attributes from the data file, right? Same like yesterday. And then it says this. It says trial 0. Means that there's going to be more trials, right? So trial 0, if you look carefully, that right here is the original tree that we built yesterday. That's the same identical guy, right? OK. Now, let's see what's after this. Ooh, there's trial 1 and trial 2. So you see trial 1 is a completely different tree, right? Now remember, how did we obtain trial 1, right? How do we get that other tree? Can somebody tell me? Do you remember that boosting algorithm we just talked about? So what happened was you looked where the other tree made mistakes. So let's say here it made a mistake, right? 5 mistakes. Here it made no mistakes, and there's more mistakes higher, right? What it did then, it said, aha, now I'm going to add a weight. I'm gonna put greater value on the ones that I made mistakes on. So what does that mean? What that means is that when you have the original tree, right? You have your tree, right? This is some attribute. This is some other attribute, and so on. I'm just making up a tree. Let's say this is some value. What happened is that, let's say inside of this leaf, you made mistakes. So let's say you have dots and stars. Now, the guy who is a star is going to have a weight. They all start with 1, right? So in the beginning, the first tree, no weights. They're all 1. Doesn't matter. The second iteration, right? If you remember what we were doing in that 2-dimensional example yesterday, let's say there are some stars and stars and stars and dots. So when you were making possible decisions, when you were evaluating these possible decisions, how to split the space, right? When you were computing the information measure of separation, right? Which was something like P ln P, or times something else or whatever else. P being the purity, right? Purity is the fraction of the number of instances of one type to the total, right? So because now these guys are weighted, so this guy might have now a weight of, I don't know, 1.5, right? As opposed to 1. So what that means is that when you make that calculation, the numbers are going to be different. It means that because you've introduced weights to these individual examples, your measure of how far things are, how much you're separating your two classes has changed now. So even though they're all in the same place, because you have a weight now, then the trees are going to come out different. Right? Does that make sense? It's a very sort of fine point. So if you're not sure, then if you want me to, I can try to explain you again. So did everybody understand this part? Okay. So the point is that now we've introduced weights. And oh, thank you. And so now every time you're going to build a different tree. So this guy is a new tree. And the reason he's different now, by the way, notice that now these guys are fractional. Right? Why are they fractional? Because there are weights on these events now. Right? So you can see that here, it doesn't mean that you're no longer making mistakes. You're still making mistakes, plenty. But now, where you make mistakes is different. Right? No. That's the whole idea. The idea of this weighting is not to reduce the error of the next iteration. That's not the idea. The idea, and you will see that in a sec. Actually, let's come back to this question in like 2 minutes. But what it does is says, focus on the place, on the space in my parameter space, focus on the area where I've made mistakes previously. And then it's a way of getting a variation, of getting a different classifier out of the same space. Right? Okay. No, the weights are inside. The weights are computed by the algorithm, but they're actually just that formula I showed you in the algorithm. Yeah. Any questions? Okay, so let's go down, and you see now there is at the next trial. Trial means iteration, right? It means that the second trial, you make yet another tree, and then another tree, and another tree. And this guy is supposed to go for 10, right? This guy is going to stop at 10, just by default 10. So you see some of them are bigger, some of them are deeper, other ones are smaller. Well, let's get to the really interesting part. Let's get to the evaluation piece right here. So, by the way, note, this is evaluation on training data. Remember from last time, it's going to be a little more optimistic than reality, but let's look at that first. What does that say? This says that trial 0, that's the original tree. That guy had 9 errors. Remember, just like last time. 9 times he made mistakes. 6 times of one type, misclassification, 3 the other. Right? So that's what we started with. 1.8% error. Look at the next iteration. The error went up, to answer your question. Right? So actually, the second guy, who looked pretty simple, his error was, quite big, 7.6%. You would know, why in the world would I do that? Why would I make myself a worse classifier? Remember, we're not after a single classifier. We're after an ensemble. We want a strong ensemble. And sometimes it means that ensemble includes all the instruments, and having that additional instrument, which by itself is not great, but as part of the team, it's going to actually help. And let's look whether that's the case. Now look at the second guy. He still has a bunch of errors and so on. They all have errors. Actually, only here in the 9th trial and also in the 4th trial did you even approximate that original tree in terms of the errors, right? So now you've built 10 of these guys, none of them as good as the original, right? But then look at what happens when you apply them all as a weighted ensemble, and that's over here. You see, your overall error went down from 9 to 3, which is now 0.6%. So at least on the training data, it seems to work. Right? Now, the real question is, what happens to the test data, right? The ones where we haven't seen yet. So let's look at that, since we have that. So you can see, by the way, the new confusion matrix says, I got almost all of them right except for these 3. So you clearly have done better on the training data. Now, let's look at the test data. And here is that. And then remember, we had 199 cases. So if you remember, the test data was worse, right? There were 11 errors. It's about 5.5%. And then you can see, same story. Only these, this classifier and this classifier even got close to that number. But when you look at the real result, which is right here, the error that you have went down from 11 to 9, right? So, so you shaved off a whole 1% in this case on your error, and that's the key point. The key point is that we didn't make a smarter classifier. What we did is build a stronger ensemble, right? And that's something you will see time and time and again, that ensemble of classifiers is very likely to outperform a single classifier, at least with most of them. So, yeah, any questions so far? No? Okay. I think this is a good place for a break. So let's have a little break. Yeah. Oh, wait, one question before. Yeah, yeah.
The boosted tree is made of one of the 10 previous decision trees?
Yeah, so the boosted tree is an ensemble, a weighted ensemble of these 10 trees. All of them. So one of them says, so you put the data through each one, right? And one of them says cat, or cancer. The other one says not cancer, cancer. And then you look at the majority, basically. So altogether, by the way, if you've ever seen this, I don't know, there's this TV shows, where you want to become a millionaire or some or another, and there's this poll the audience part. If you ask one person whether they know something, okay, the odds are, who knows, you may be lucky. But if you ask 100, maybe the odds are a little better. Right? Because that's just how that works. Because we all know something a little bit different, but altogether it's good. Yeah. Other questions? Yeah. How did you make the ensemble? Did you understand how we made each one of these? So you basically, there's actually a couple of ways you can do it. One is you can just ask for a majority vote. You can just say, you guys all vote, and we're going to take the majority. Simple average, right? If you want to do a continuous, simple average. Other types of boosting algorithms, there's several types. Okay, they introduce also some weights that you can tune, even. Something I will talk about. Let's take a break, and then I'll tell you about actually a related, a completely different classifier that you can build out of this. So I'll let you think about how that's possible. But we'll do that right after. Well, maybe let's say 5 minutes. 5 minutes break. Okay. Oh, we can also try and fix your, if you like. goal from cross-validation? Well, it is different because there's one similarity, right? The similarity is in bootstrap, you just take similarity. The difference is that in some cases it's random, right? In this case, it's not really random, right? So I'm going to split it up in equal sets, and I'm anyway going to train on. Okay? It's not, but it is. There's definitely. But the goal is different. In the bootstrap case, what you're doing is actually you're trying to find and classify and reduce. Here it's all about this fidelity. You're not trying to find anything better. By the way, one thing that also happens when you do hyperparameter tuning, so-called hyperparameter tuning, is they also often do it together with crossfire. That's something that people do. It's not a bad practice. But still remembering that you need to keep getting another data set. Now I'm trying to remember, I think we're still at an hour break. So maybe let's just have a break, and then we'll come back.
Pero
Okay, so can everybody hear me okay? Good. All right, so let's kind of remember where we were. We talked about classifier performance, right? So we looked at this receiver operating characteristic curve, ROC, right? We're going to use the area under this as a measure of how well we're doing. If that number is close to 1, then you have a great classifier. If that number is close to 0.5 or below, God forbid, then you're not doing so hot. So you need to improve. Okay, but that's a way to kind of compare different classifiers. And then we looked at how do you actually measure that, and you do this cross-validation idea. Okay. Now, since we already talked about this, let me really briefly start on a topic that I'm going to come back to tomorrow. But I want to start. I want to get you started on this topic. So this topic I want to talk about is feature selection, right? So what's a feature? Feature is a variable, yeah? And that's a pretty crucial task if you think about it. You have a problem, and you want to figure out, how do I best arrive at a solution? And part of that process means I'm going to try and identify those features or variables that are relevant to the problem, which are going to be your ingredients, right? That you're going to build these classifiers from, or if you're going to build classifiers from just raw data, whatever the data is that you measured or measure, you want to be able to extract useful features, right? So today, I'm not going to talk about feature extraction. We're not going to talk about that. We'll talk about that tomorrow. Feature extraction means how do you extract features from the data. We're not going to talk about that. Today, we're just going to talk about actually, how do you evaluate the relevance of features? Something important. How do you figure out, how do you even select them in the first place, right? It's more of an art, actually, right? So let's talk about that. Now, it's crucial. If you're doing some sort of data analysis, you put in garbage, guess where you're going to get out? Garbage, right? So one of the very crucial things is to figure out, what is the stuff that's relevant to your problem? And that means, looking at, understanding what the degrees of freedom is of your problem. What do you think is relevant? Sometimes the things that are relevant may not be obvious. That's why you need to be able to evaluate them. That's why you need to extract them. If everything was obvious, we wouldn't be here, right? Talking about this. But what you want to look at is how relevant these things are to the problem. And the other part that many people ignore, but you should never ignore, is how well do you actually understand that feature? What I mean by that, what is the uncertainty on that feature? How well do you actually understand it? How well does a thing make sense? Can you model it? How well does it correspond, if you have simulations, how well does it correspond to real data? That's an important thing. Now, we'll talk about the questions of uncertainties a little bit later, but this is something to keep in mind. Finally, the thing you want to worry about also how powerful it is. If your goal is to classify things, how well does that feature, how well is that feature going to contribute to that? How powerful it is? But also, its relationship with others matters. Why? Because we're not doing univariate analyses, right? You're not just going to do stuff with that one variable. They all have to interact, play together, work together. So how well it interacts with the others matters. So typical thing people usually start from, they usually, do some basic measurements that you try to cover the phase space of your problem. Like in the breast cancer set, it was maybe, you deal with cells, you looked at the size of the cells, you looked at this different things. You try to cover the phase space as you know it, as you measure it. In physics, it could be, your actual physical, since we're talking about particles and whatnot, so you look at the kinematics, so-called kinematics of your processes, right? How fast things are going, what are the angles between them, that kind of thing, right? So you can build, more complex features, right? And the idea there is you introduce some domain knowledge, right? Maybe in the breast cancer data set, some of these variables, they weren't trivial. Maybe doctors with years of experience, and they said, oh yeah, I did notice when I looked at these pictures that the patients that happen to have, I don't know, an increased something, are likelier to have cancer. So domain knowledge plays into this. And these are so-called high-level features, right? Usually they come from experts, right? These experts says, this variable is going to be really, really good to discriminate whatever it is you want to discriminate, right? So I don't know. If you're discriminating, I don't know, between cats and dogs, I'm sure there is one feature you can pick out. It's going to be really, really good to discriminate to them. Sound, right? You can figure them out almost unambiguously, right, by their sound. But okay, I'm sure there are other ways. So if you're going to do visually, there'll be other features. But anyway, you get the idea. But the point is that usually these are one-dimensional. And when people evaluate them, they evaluate them in one dimension because they're only looking at that feature, right? This is a natural thing to do, but of course, that absolutely ignores this, right? You ignore how they interact with each other. And that's something to keep in mind when you're actually evaluating features that you're going to be using. So sometimes people do something called feature engineering. They try to combine features with each other to arrive at better features, more features, whatever. And that thing starts to explode, right? It can grow real quick. Typical problem with, I don't know, 20 or so features, you start doing this, you're going to be in thousands pretty fast. And as you know, the more features you have, the longer the whole thing takes. And you know, there's some considerations to be said about that. But I can tell you that there's plenty of data sets that have hundreds of thousands of features, right? So that's not anything revolutionary. But most problems don't have that dimensionality. So you want to balance somewhere in this, right? Now, let me talk about this for a sec. There are different methods that you can use, or different classes of methods you can use to select your features. Let's say your goal is to rank your features. Let's say somebody comes in and gives you the features. It says, here is my set of features. And you want to figure out, you know, what if, I think I see some of their talks, and they try to, like, you know, reduce the feature set, you know, to make it manageable in some way. And there's many different ways you can do this. The simplest way is called filters. Filters means you make the selection based on some, I don't know, some basic correlations between them. You don't actually make any classification models out of them. So you do it before building the model. You do some kind of a pre-selection. Is that accurate? No, it's not accurate. It's one of the least accurate things you can do, but it's quick. So people do it. What is more accurate? Something called a wrapper. You know, like a wrapper, you know, kind of like a candy wrapper. The idea is that just like wrappers go around the candy, in this case, you build the model, and they sit sort of on top of that, right? So you build the models, and you look how well the feature contributes to that building of that model, and then you say, aha, this guy was good, and this guy wasn't good, and so on, by guy, girl, whatever, the feature. And the point is that this feature selection is really not kind of, you know, you need to build the model. So it's more accurate, but more expensive, because now you have to go and build these models, whether they're BDTs, neural networks, whatever it is. So accurate. So that's a trade-off. Quick, not accurate. Accurate, not quick. Then you also have things which are in between, like probabilistic wrappers, right? That are quicker, but also they're a little less accurate, but still okay. So there's different methods people do that. You know, like, you know, kind of like hill climbing. You kind of go in one direction, you add another feature, see how well that does, or you subtract, you go in the other way. There's different ways of doing it. But in the end, they're still wrapper methods, and they're preferable because of the accuracy. Then there is something else, and that's this embedded hybrid method. And I'll just touch on that now and come back to that tomorrow, because it's also relevant in the context of deep learning, something we're about to get to now. And the point is that here, your feature selection actually happens inside of the model building process. So as you're building the ship, as you're training the ship, you actually kind of, you know, go and change it, right, to make it better. So the idea is that you start with some features, but as you go along, right, something's happening. You know, some kind of a feature extraction or selection is happening as you're training the algorithm, right? And I'll give you some example of this. Maybe I can give you already one example. But the general idea is this. So wrappers, as I said, more accurate. They can assess these interactions between features. By the way, features interact in this context. Think of even the simple decision tree. Do you remember that at every decision node there was a competition, right? Imagine that you had some features that were really similar to each other, really similar. And what would happen is that sometimes, you know, one of them would win as opposed to the other one, but it would be really, really close within some error. So what you end up with, you know, is you would say, ah, he won. He's the one. But in reality, you had another feature really similar to him that didn't win for some whatever reason, you know. And then some other time, the other feature is going to win. So it introduces noise. And that's, of course, not the best thing you can do. So the point is that But the important thing is that if you do it this way, you can actually assess these interactions, and you can find an optimal subset within this. There's all sorts of types. There's a whole branch of data science that evolved to this area. So there's methodical, probabilistic, heuristic, kind of forward, backward. You add stuff, you subtract stuff, you kind of walk around, you try to find this sort of optimal subset. That's all it does. Now, here's an example algorithm. Now, example wrapper. Here you introduce some kind of a performance metric for the algorithm. Let's say it's the area under the ROC curve, for example. And then what you do is you throw dice. You throw dice, and then you look at different subsets of these features, and you figure out how much did that feature contribute to that classifier's performance. How do you do that? Many different ways. You can look at how it participated in the process, or what you could do is actually remove the feature entirely and see what happens to the classifier performance. Performance goes down, that feature actually contributed something useful, right? Performance goes up, oh man, that was a bad idea to include it, right? So that's one way to actually quantifiably measure the contribution of a feature to that process. So then you can get some kind of a ranking, right? And then you can say, oh, this guy is really relevant. This guy is irrelevant. You might even get some negative guy, right? Some negative feature. You're like, whoa, why did I even add him? He's just introducing noise and problems. So you'll know who to remove. But the point is, this is just one example. You can make it probabilistic. You can make it fast. Doesn't have to be exhaustive, for example. Now, this is what I was telling you about earlier. It actually has a name. It's called feature selection.